times C is 1, so we have C is 1, L is 1, we still want to clear C. So that's done. So that's register C. And now for D, we can just do the exact same thing. We basically have, if I can get my circuit out here, I basically have two inputs, S and L. And why not just make that a mux again? And so when L is 1 and S is 0, we do a parallel load, and when S is 1 and L is 0, we do a shift. And then when they're both 0, we just hold. So we're going to do that. SL 0, 1, 2, 3. This is 4 to 1 mux over here. Probably should be complete. 4 to 1 mux. And that goes into here. D, Q, Q bar. D, Q, Q bar. D, Q, Q bar. And we shall call this one QA1. No, sorry, this is going to be QA2. This is QA1 and QA0, just to make life easier. And so when they're both 0, we want to hold the value. So QA2. When load is 1 and shift is 0, we want to take in the value from the ALU. So for lack of a better choice of things, I'm just going to call this Z, and this is going to be Z2. And then we're going to have this one, when shift is 1, L is 0, we want to have QC come in, and when we have both of them high, well, that's never going to happen if you look at this, because C and S and L are never both 1 in any of these states. So we can ignore that, or just, if we want to protect ourselves, put QA2 in. It really doesn't matter. Same thing here, pretty much. 0, 1, 2, 3, SL, S1, S0, S1, S0, 4 to 1 mux. And I'm going to put QA1 into here, Z1 into here, QA2 into here, and into this one goes QA1 just to protect ourselves. And one last one, 4 to 1 mux, S1, S0, SL, 0, 1, 2, 3, 4 to 1 mux. And then this is QA0 into here, Z0 into here, Q, and then this is our shift, so this is QA1, and this one is QA0. And then for part E, again, we're just basically choosing between a shift register and a parallel load, and so why do anything complicated? We will just do the exact same thing one more time. So E, D, Q, Q bar, Q, Q2. Maybe not the best naming convention. You'll have to forgive me. Q bar. This is Q, Q1. And over here, we're going to have D, Q, Q bar. Sorry, I probably should put a clock in on these. Q, Q0. Clock onto this. And another big 4 to 1 mux. 0, 1, 2, 3. S1, S0, SI, 4 to 1 mux. When we have when we 0, we don't want to change anything, so Q2 stays the same. 1, that's when we initialize, so we're going to want to take in 2. With this, we're going to shift, so we want to take in QA0. And then with this, well, this is never going to happen, but we'll just do QQ2 just to be safe. S1, S0, 4 to 1, mux, S and I. So this is going to be QQ1, in 1, QQ2, and we're going to keep this one the same. 0, 1, 2, 3, S1, S0, S and I. We're going to put Q, Q, 0 to keep it when we don't do anything, and 0 when we want to do the parallel load. When we want to do the shift, we do Q, Q1, and for this final one, we just want to keep things the same, so we do Q, Q0. And that's parts A through E, and for F, I need to grab another sheet of paper. F is just the ALU, which frankly is pretty simple. So we're going to have, basically, our functionality is when k is 1, z is outputting 0, and when k is 0, we're outputting a plus b. So really, what is this? It's just an enable. When k is 1, we disable. K is 0, we enable. It's just kind of a flipped enable. And so, basically, all I'm going to do is do my full adder, A, B, C in, C out, and sum. And I'm going to do 2 more full adders. We're just going to treat these exactly the same way. C in is going to be 0 on this one. Let's feed into each other. And then the sum bit is just going to get ANDed with k bar. And this is just going to get ANDed with k bar. ANDed with k bar. So this is Z2, Z1, Z0. And C out, if you want to, you can AND this. It really doesn't affect anything, but just why the heck not? K bar. This is C out. And so that completes problem 1.